Hi everyone, my name is Yin-Jyun, and the following will be me presenting unsupervised disentanglement of pitch and timbre for isolated musical instrument sounds. This is a joint work between SUTD, A*, and AIST. Let's start off with the disentangled representation, which allocates distinct vectors of variation into separate dimensions of a representation. For example, we can describe an isolated instrument sound with a pitch and a timbre variable. Under such a formulation, we can learn interpretable feature representations which are useful for downstream tasks, such as sound generation and classification. The encoder here can be the neural network. So the question that we ask in this work is that can we learn the two vectors without the labels, without any supervision, as opposed to the supervised approaches? The generative process that we have here is that a note recording is generated by the two independent variables. One is the pitch, the other is the timbre. And we model the pitch as a discrete latent variable because we have each note recorded as one of the 12 pitch classes on the equal temporal scale. And such a architectural constraint would encourage the model to allocate the pitch information in the discrete latent variable and the rest to the continuous latent variable. For learning, we use the variational autoencoder as the backbone algorithm. And under such variational inference framework, we have an approximate posterior distribution, a factorized one to be specific, to approximate the true posterior distribution. And in order to allow stochastic gradient descent, we do reparameterization tricks for both of the continuous and discrete latent variable. To improve further the disentanglement, we can impose more regularizations with self-supervised learning techniques. So the main assumption here to allow such regularizations is that a moderate shift of pitch does not alter the timbre of the original musical instrument sounds. So we can create pseudo data pairs, which are the original sound sample and the pitch shifted version. Accordingly, we can impose extra constraints on top of the multiplicative function elbow that we have seen. For evaluation score, we propose a quantitative metric, which is a consistency diversity score. So to be specific, the consistency concerns the posterior distribution of a pre-trained pitch classifier, which says that such a posterior distribution should be consistent given a fixed pitch variable, regardless of the timbre variable Z. On the other hand, the diversity says that the aggregated posterior distribution should be uniformly distributed because now that we are conditioning on different pitch categories. So the summarized CDS is the average of the KL divergence between these two distributions. Note that this score is similar to inception score. Please visit us for more technical and evaluation details. Thank you.